Welcome back. Um, I want to talk about a couple of topological concepts that we're going to be using. First of all, let me define what we call open ball and closed ball. The so in R2 an open ball is an open ball centered at C is basically disk of radius disk of some radius r without the boundary circle. So if you look at this disk of radius r centered at C without the boundary circle, now the points in this disk satisfies the each point on this disk satisfies this inequality, that is the absolute the length of x minus c is less than r, because the length of x minus c, that's the distance between x and c. So the distance between x and c must be less than r. So this inequality right here, this is the set of all points x such that the distance from x to the center C is less than r. So this is giving us a disk of radius r centered at C without the boundary circle. This is called an open ball in R2. Now, what's a closed ball in R2? Well, it's just an open ball where the boundary circle is included in the set. So this is the set of all x such that the distance from x to c is less than or equal to r. So either x lies on the boundary circle, or x is inside the circle. So this is a closed ball. Now in R3, an open ball is a sphere. A sphere is a solid sphere without the boundary points. So again, we can use the same inequality to describe an open ball. So this is an open ball centered at C with radius r. So you're looking at all the points x where the distance from x to the center is strictly less than r. So again, this is describing all the points inside the sphere, and it doesn't include, this set does not include the points on the surface of the sphere. And the closed ball means it's a solid sphere with the boundary included. So generally, what is an open ball? So in R to the n, an open ball is the collection of all x in R to the n such that the distance from x to some c is strictly less than r, where c and r are fixed. And the closed ball is the collection of all points in R to the n where the distance from x, all points x in R to the n where the distance from x to c is less than or equal to r, where c and r are fixed. So this is giving us a closed ball, this is giving us an open ball. Okay, so what's an interior point what is an interior point of a subset of R to the n? So if I take S a subset of R to the n, we say that P is an interior point of S if there is an open ball B centered at P such that B is completely contained in S. So if you look at the point, if you look at this region here, within this boundary curve, then this region is what I'm calling S. And if I take a point P right here, this is an interior point because there is an open ball centered at this point that is entirely contained in the set S. So if I have this subset of R to the 3, then you can see that so here I'm picking the subset S to be like a box in R to the 3, and if an interior, so P here is an interior point because there is a open ball centered at P that is entirely contained in S. However, notice that Q in each of these figures is not an interior point because no matter how small of an open ball I pick centered at Q, that open ball always contains points from outside of S. Same thing happens in the second figure. No matter how small of an sphere I pick centered at Q, that sphere will always contain points outside of the S, outside of the set S. So Q in both figures are called boundary points of S. So a point Q is a boundary point of S if every open ball centered at Q includes points in S and also points not in S. So if you look at the point Q in the first figure, notice that any open ball centered at Q will always contain points from S and points outside of S. Same thing in the second figure. No matter how small of a sphere, every sphere centered at Q will contain points from inside of S and points from outside of S. So these are boundary points. We say that S is an open set if each of its points is an interior point. So if every point in S is an interior point of S, then we say that S is an open set. We say that S is a closed set if it contains all of its boundary points. So here are a couple of examples. So the first figure right here, this is an open set. So here you see that none of the boundary points are included in the set. So each point here is an interior point. In this figure right here, notice that all the boundary points, because I'm using solid curve here, it means that all the boundary points are included. So this is going to be a closed set. This one is neither closed nor open because even though a lot of the boundary points are included, some of them are not included. So you see that it's not going to be closed because some of the boundary points are not included, but at the same time it's not open because there are some boundary points in it. So it's not going to be open. We say that S is a bounded set if it is contained in some ball centered at the origin. So if S is a subset of the 2 space, then we say that S is a bounded set if you can enclose S within a big circle centered at the origin. And if S is a subset of the 3 space, then we say that S is bounded if we can enclose S in a big sphere centered at the origin. So that's what we mean by a bounded set. So what it simply means is that the distance between the origin and the points in S is bounded, right? the distance between points in S and the origin is bounded. So in my examples here, the triangular region here, this set, so here the set is all the points on the triangle and inside of the triangle. So this is a bounded set because we can always enclose it in a big circle centered at the origin. But if you look at the region, which is a vertical strip here, so it goes up forever and goes down forever. So this region is in between these two lines. This is an unbounded set because no matter how big of a circle I pick, I am unable to enclose this set within that circle. You cannot enclose this set in a circle centered at the origin. So this is an unbounded set here, and this is a bounded set here. Okay, so that's all I need at this point on these topological ideas. And in some of the statements, I'm going to use these words. All right, so I'll see you in the next video.